Good morning. So we can continue with uh, classical thermodynamics. So far we have seen thermodynamic functions like entropy, Gibbs free energy, Helmholtz free energy, etc. Okay. The thermodynamics that we had been dealing so far had been thermodynamics of closed systems. What is a closed system? A closed system is one in which there is exchange of only energy with the surroundings. There is no exchange of matter with the surroundings. But when we consider an open system, there is exchange of both matter and energy with the surroundings. That means in closed systems, the composition of the system does not change with time. But in open systems, the composition of the system may or may not change with time. Hence, the thermodynamic properties that we study, entropy, enthalpy, free energy, these are all extensive properties which are dependent on the composition of the system or the number of moles of the system. Okay, so when we consider open systems, we have to consider the fact that the system composition may or may not change. Accordingly, these properties, the extensive properties, may also change with change in composition of the system because they are dependent on the composition of the system. Hence, the thermodynamics that we had been dealing so far is not adequate. So we have to find expressions for these extensive properties for open systems. So now we'll deal with thermodynamics of open systems. Okay, to convert the thermodynamics of closed systems to that of open systems, we need a new property known as partial molar property or partial molar quantities. Okay. So far, we had been dealing with a thermodynamic function x, a thermodynamic function x as a function of only two variables, either pressure or temperature, or volume or temperature, or pressure or volume so far. Okay. So, but in open systems, we have to consider one more variable, that is the number of moles present in the system. So we have to write x as a function of pressure, temperature, as well as the number of moles in the system. Okay, the system may contain more than one type of particles, and hence we may have to write it as x is a function of pressure, temperature, N1, N2, etc., Ni. Okay, there are so many types of particles. So each one has its own number of particles. Hence, we have to write N1, N2, etc., Ni. Where N1, N2, N3, what are those? They represent the different quantities of various components which may be labeled as 1, 2, 3, etc. in the system. Okay. So in this case, we'll write d, if we can write x as a function of p and t, we can write a small change in dx may be represented as dou x by dou p at constant temperature into dp plus dou x by dou t at constant pressure into dt. Okay. So for open systems, we have to write dx as equal to dou x by dou p at constant temperature and number of moles of all the components into dp plus dou x by dou t at constant pressure and the number of moles into etc. Ni into dt, and new term comes dou x by dou Ni, which will be at constant pressure, temperature. N1 is varying, so N2, N3, etc. Ni into dni plus the next term dou x by dou N2 at constant pressure, temperature, N1, N3, etc. Ni into dn2 plus dou x by etc. It goes on. Okay, goes on and etc. And the last term will be dou x by dou Ni at constant pressure, temperature N1 into etc. Ni minus 1 into dNi. Okay, so we have a large number of terms in the expression for dx, which represents a small change in the thermodynamic function. Okay, in this equation, dou x by dou n at constant pressure, temperature and other number of moles Ni, Nj, this quantity may be represented by x bar I, and x bar I is known as the partial molar property or partial molar quantity. Okay, so dou x by dou Ni is represented as x bar I. So if it is dou x by dou N1, it will be x bar 1. Okay, then this expression becomes dx is equal to dou x by dou P at constant temperature N1, N2, etc. Ni into dP plus dou x by dou P at constant, dou T at constant pressure N1, N2, etc. Ni into dt plus the next term we can write as x bar 1 into dn1 plus x bar 2 into dn2 plus etc. x bar I into dni. Okay. Suppose we are considering the open system at room conditions. Okay, normal conditions. At normal conditions, pressure and temperatures remain constant. In that case, dP is 0, dt is also 0, and hence this equation becomes dx is equal to x bar 1 dn1 plus x bar 2 dn2 plus etc. x bar I dni, where x bar I is known as the partial molar property or partial molar quantity. If we are considering entropy, then this equation becomes ds is equal to s bar 1 into dn1 plus s bar 2 into dn2 plus etc. s bar I into dni. If we are considering Gibbs free energy, dg is equal to g bar 1 into dn1 plus g bar 2 into dn2 plus etc. g bar I into dni. If we are considering enthalpy, then the equation is d enthalpy dh. dh is equal to h bar 1 into dn1 plus h bar 2 into dn2 plus etc. h bar plus h bar I into dn. H bar I is known as partial molar enthalpy, S bar I is known as partial molar entropy, and G bar I is known as partial molar free energy. And the partial molar free energy is called the chemical potential mu I. Chemical potential mu I. Okay. So what is mu I? Mu I or the chemical potential is G bar I, or it is dou G by dou Ni at constant pressure, temperature and N1, N2, etc. Ni minus 1. In some textbooks you will find it as Nj, but we can write Ni minus 1. The terminology that we will use is I minus 1. Okay, Ni minus 1. This is chemical potential. This term you might already have studied in your degree classes. This is chemical potential. which is the partial molar free energy. Partial molar free energy. There is a physical significance for this chemical potential. Now let's see what the physical significance of chemical potential is. So in order to know what the physical significance is, let's write what is mu I. Mu I is equal to dou G by dou Ni at constant pressure, temperature, N1, N2, etc. in I minus 1. So what is mu I? If dou Ni is equal to 1. What is dou Ni equal to 1 means? We are adding 1 mole of ith component to the system. Okay, we are adding 1 mole of the ith component to the system. Okay, if dou Ni is equal to 1, mu I is equal to dou G. What is dou G? Change in free energy. So what is chemical potential? It is the change in free energy produced by the addition of 1 mole of the component. 1 mole of the component at what condition? At constant pressure and constant temperature, as well as the other molecules of the system. Okay, so it is the change in free energy produced by the addition of 1 mole of a component at constant pressure and temperature. In order to define this term, we'll say at constant temperature and pressure to a large bulk of the system so that its composition does not undergo any change. Okay, it is the free energy change produced by the addition of 1 mole of a component at constant pressure and temperature to a large bulk of the system so that its composition does not undergo any change. Okay, suppose there are no other components present. That means there is only one component, N1, N2, etc. All of them vanish. There is only one component, and hence we can write mu I is equal to dou G by dou N at constant pressure and temperature. Okay, so what is mu I now? Mu I will become equal to dou G at constant pressure and temperature when dou N is equal to 1. Okay, dN is equal to 1. So what is chemical potential of a pure substance? It is the change in free energy at constant pressure and temperature. Okay, if we are considering 1 mole of a pure substance, free energy is identical with the chemical potential. Free energy change is identical with the chemical potential. Okay, chemical potential, the definition is it is the change in free energy produced by the addition of 1 mole of a component to a large bulk of the system at constant pressure and temperature so that its composition does not undergo any change. We have to keep all other components constant. That's why we are saying the composition does not undergo any change. Chemical potential is the free energy change produced by the addition of 1 mole of a component to a large bulk of the system at constant pressure and temperature so that its composition does not undergo any change. If we are considering a pure substance, we are considering 1 mole of a pure substance, it is identical with the free energy change. Okay, it is identical with the free energy change at constant temperature and pressure. It is also known as the escaping tendency. Escaping tendency of the system. Chemical potential is also known as the escaping tendency of the system. Okay, now we have seen what chemical potential is. Now we will see what happens to the chemical potential with temperature and pressure.